So it finally happened. I give you the option of being virtual or come into class. And if I could turn the camera around, I will, but I'm talking to an empty room. So feel free to chime in so I know you guys are there. I think because of that, we'll make next week's class for all virtual, even though it's not all virtual on the schedule. So for attendance codes, the in-class attendance code is 1606. The virtual attendance code is 4356. So once again, in class 1606, virtual 4356. So we're 2 weeks from the midterm. So I'm going to finish the slides tonight. Next week, like I said, will be all virtual, and it will just be a review for the exam. Before you ask, the exam is only from the midterm on, only material from the midterm on. You know, some of it's a little cumulative, but for the most part, it's just from the midterm on. So we're going to go through the rest of the slides tonight, and next week in a virtual session, we're going to review for the exam. And then 2 weeks from tonight, May 4th is, May the 4th, get it, is the exam. The exam will be like last time. I'll talk more about the logistics of it next week. Okay, so a couple things tonight, 3 actually. I said that we're going to do this HDL code generation and verification. This is similar, but more general than the RISC-V stuff that I talked about a couple weeks ago. It's very practical. It's something that you're more likely to do for a generalized design. The RISC-V stuff was a limited example. It showed the concept, but in a very specific application. Not that there was anything wrong with that, but it's done, right? You would just bring that into your design as a whole. And then we're going to talk about verifying asynchronous circuits, which you kind of touched on here and there, but it's a good time to just kind of put that together. And then what's labeled as lecture 14, it's only a few slides, is the verification business, which is kind of interesting. I'll tell you what my motivation was for putting that in as well. Okay, so started. So this paper, I got this from Generating, Optimizing, and Verifying HDL Code with MATLAB and Simulink. So let's put a little background on that. HDL Coder, which is a tool, is something that allows you to create a MATLAB program, a .m program, or a Simulink picture, right? The block diagram in Simulink. Careful with this. Press a button and generate code. Does it work? It does and it doesn't. So like anything, the tool itself, the language itself, doesn't guarantee that you're going to be able to produce some that is even possible to be built. And that's what happens with these code generation tools, is the people who are expert in their specific field aren't expert in chip design. So there's a concept of synthesizable Simulink. So my experience with Simulink is not as a system designer. It's working with system designers so they can produce synthesizable code out of what they're developing. Because inherently, tools like MATLAB and Simulink are behavioral tools. So you might feel what's coming here. So that real need to produce synthesizable code makes it difficult to use MATLAB, Simulink, HDL Coder for design, for synthesizable designs. But we don't care, we being verification, because in verification, we worry about behavioral code and the behavior of the stimulus and the behavior of the response checking. So this is perfect for us. And I don't think it was originally intended this way, right? When they were developing this, they were developing it like, hey, here's a shortcut to synthesizable code. And the reality is you still had to be a digital designer. But in the verification side, it's not as bad. And we'll go through the example. So you'll see this picture multiple times with different details in it. But It starts out with a set of requirements. Isn't that convenient, right? That's what we started out the class back in January. And then we go through some behavioral phase, right? So this research and design, we're not trying to build something. We're trying to construct a system that has the performance characteristics that our requirements are outlining. We're not worried about something that can be implemented. Now, this arrow right here might imply that once you have your behavioral code, that you can press a button and you can get three things. You can get C, potentially. So there's also something called autocoder. Sorry. An autocoder is something that does the same thing, but in the software world. So what autocoder does is you write your Simulink MATLAB definition of the design, you press a button and it puts out C code, right? So it's something you'd run on a processor. In the FPGA ASIC world, a lot of times we're looking to produce HDL, so VHDL and Verilog. And that works well too, and it actually does produce this code. Or we can have structured text. The example of structured text that I showed is Chisel, right? So the specification that's written so it can be synthesized and it can be used as a test bench. So don't worry about the left-hand side. This is stuff that you use to run this. And I'm not too worried about the desktop side of things. We're right on this column here. So here's the problem. Here's the problem when it comes down to digital design. So in digital design, we work with gates and flip-flops. Gates and flip-flops are logic elements and state elements. State elements need clock and reset. This tool doesn't understand clock and reset unless you impose it on the tool. So even when you write a state machine in Simulink, it just changes state when the proper event happens on the inputs. So you have to make it a clocked state machine. Now, we don't have a clock per se that clocks our test bench. And you think, well, yeah, we do. Well, we generate a clock, but the stimulus uses that generated clock to time its stimulus. So if you remember back, I said, don't just use pound delays to time things in your test bench. Use pause edge clocks. So the test bench is cued off of the edges of your clock. So the timing all comes from the same clock. So now we can do that same kind of thing by creating behavioral code with MATLAB for our test bench. Now, one thing to look at, and hopefully you've seen this already, this path right here, this outer path, which is the verification path, right, for our purposes, is seeing if the design matches the spec. Sound familiar? Right, that was the first hour of class probably. I had already said that, if it even took me that long back in January. So this takes that very fundamental concept of verification and applies it to this high-level tool. So you hear about high-level synthesis. And high-level synthesis is something that works within a controlled environment, right? Like Chisel, like signal processing, where you can generate signal processing elements and put them in a line, which is something that's very much part of how MATLAB works and where it works well. But in general design, it doesn't work well. It's hard. It's much easier to just write the HDL. But in verification, there's a lot of time involved, and we're not as worried about the architecture, if we're worried about it all. So we can generate this. Now, you might end up having to generate a behavioral model of the design to be able to generate the test for it, to be able to generate the verification suite for it. So some of this stuff I've already talked about. So we have MATLAB, and we can use, I called it autocoder. On the slide, they call it MATLAB coder. They change the name over time. And the HDL coder to generate on the left-hand side C code that will run on a processor, and on the right side, HDL that will run on an FPGA or an ASIC. One thing I hadn't said yet, this picture. What do we do with C code? We run it on the processor. Where do we put the processor? On the FPGA and the ASIC. So there's a maybe implied convergence here that these components right here are inside the FPGA and the ASIC. So you can have both of these tools, right? You have one design, both tools that generate something that goes onto one piece of silicon, whether that's an FPGA with a hard processor or a soft processor on it, or an ASIC that you've compiled the processor into. I'm sorry, yes, an ASIC that you've compiled the processor into. And what this does at this point in time, and we're getting a little away from verification for the moment, but what this does is it allows you at the high level, right, the top block there, the MATLAB block, to do your hardware-software trade-offs. And hardware-software trade-offs are the thing that tunes your design to be as efficient as possible, right? You have performance requirements, and performance requirements include things like latency and MIPS and things like that, the actual performance of a processor or the latency of a calculation. But you also have performance characteristics like size. So for a given performance envelope, you want to create the chip that's the smallest size because area is proportional to cost. The other piece, and it's related to size, is power. So if you can do hardware-software trade-offs to allow you to save power, again, another win. So having one place to implement your whole behavioral algorithm and then deciding what gets put into the processor and what gets put into the logic is advantageous. Now you might be looking at this and think, how does that exactly work? It doesn't work automatically. You have to do things to move things around. It doesn't automatically know that there's a processor in there. And when you pull a function out of the logic, you can move it into it. You do have the partition. The thing is, you're specifying the whole design, not in the specification. When I say specify, I mean capturing the whole design in one place. So here's an example. We'll use this example as we go through. It is just a logic example. So it's just suffice it to say, it's a digital signal processing algorithm. And it has some functions that it goes through, we'll get into a little bit. It has a stimulus and it has response checking. Now I look at this picture and I think immediately something causes me some heartburn. And the heartburn is, where's the chip? Right now, I already told you this is all logic, but if a system designer gave this to me, I would immediately give him back the drawing with a pen and say, draw a circle around the chip, because some of this stuff is stimulus. Some of this stuff is response checking. I'm not going to build an input audio wave, right? That's likely a file that's being read in. I'm not going to build you'll see what the wave device is. It's an oscilloscope looking thing. So at some point, and probably earlier, you have to differentiate between the design, the thing you're building, the scope of what's going into the chip, and the test bench. So I'm calling this stuff the test bench, the stimulus over here and the response. And so maybe now it's clear and someone could, draw a comment block around this, but there's more to it, and there's more to building a chip. And honestly, in a class that was oriented more to design, I talk about these things, but you can actually specify pins and not necessarily the characteristics of the pins. But if you're doing FPGA design, you can say, I'm going to pick on this block right here. This is a pin. I don't know what that converter does. It's not obvious from this. I could drill down into it, I could tell you, but it's not obvious. And what I need to know is what's the chip, what's the DUT in our DUV in our language, and what is stimulus and response. Notice that it is also simple stimulus and simple response. Not that it has to be that way, but it works out well. Okay, so here's a little bit simplified picture. We have MATLAB and Simulink, and it goes into HDL coder and it produces Verilog or VHDL. This is the right-hand side of the picture I showed you 2 slides ago, but it's the piece that we're using for this example, right? We don't have the software side for this example. So, model-based design flow. Now, remember, I hope I said this on the first night, that I wanted you to stop thinking about putting code into a simulator and running a test bench. I wanted you to start thinking that everything was a model and the simulator was just something that calculated those models. So the simulator is full of models of logic gates for your DUT. The stimulus generator is a model. The response checker is a model. And the simulator is a calculator. And you dump all this stuff in and say go, and it just calculates until you program it to stop or you hit stop. So that works well here. Now, what we're going to have, secondly, this works well with last week's lecture. This is kind of what gave me the idea for last week's lecture, is this particular tool is also savvy to certain reference design boards. So remember last week I talked about effectively looking at the response of something, but a little bit of generating stimulus and being able to run your whole simulation, as it would be, on a piece of hardware, on this generic FPGA. Well, that's what this is doing, but it's doing it more automatically. So we have clear models for what the design is captured in. That's MATLAB Simulink. Then from there, we go into this HDL verifier. Now, HDL verifier takes the model of the design and it allows us to create at least the shell of a test bench. So now we have a design that has stimulus and response in it. We put the RTL in, then we have this co-simulation, right? We'll get to that in a second because that's down here. And then the classic path of synthesis, map, and place and route, right? Those are the FPGA design tools. And then for verification, functional simulation, static timing analysis, and timing simulation, which is what we've been talking about. So we take this stuff, we do a back annotation, we change our model potentially, and we go through this path. Now, the other thing is we can take the implemented design and put it on an actual chip. Now, this is kind of invisible. The stuff that I was talking about last week, you were just putting your design on, and if you needed stimulus, you had to either have the ability to somewhat synthesize your stimulus generator or create a stimulus generator that was synthesizable and put that on the chip too. Here, it all comes down to this FPGA in the loop. So now the FPGA in the loop, you can implement the design and run the algorithm for the system design, all on one of their selected boards. Now, you can't just go out and buy a reference board and have it come in. It's limited. And they generally, if you're using a certain family, the biggest chip in the family that's on a reference board, that's the one that they specify. So if you look at the space of reference design boards, there's probably hundreds of them. If you look at what's available in here, there's probably tens of them. They only pick big ones, which makes sense because they want to have plenty of room. And they're also assuming that you're going to buy one or two of them because they're $10,000 a piece. I'm probably being conservative there too. So as a workflow, we do Simulink to HDL, MATLAB to HDL, right? These are really 1A and 1B. And then 3 is the hybrid workflow where we have our own design, the MATLAB design, and we bring them together to create Verilog, I'm sorry, VHDL. I'm just going to say HDL instead of saying both of those all the time. All right, so this is the HDL side, but these are more towards the workflow. Now, remember, this has to work, and it has to work when you put it on the chip. So we're thinking more about synthesizable design even for the test bench. So you write your algorithm, number one. Second is fixed point. So if you're familiar with the MATLAB Simulink flow and implementing it on FPGAs, you know that everything has to be fixed point. The floating point just blows up the design. It takes too much space. So you always have to convert to fixed point. The problem with taking, some smart person's system design that's in numbers that are, doubles, something that isn't necessarily cast to something you can put into hardware, and then casting it to fixed point is that you lose some accuracy, range and domain accuracy. So when that happens, you might not have the accuracy you need. So what you can do here is you can test your fixed point model of the design that you're building against the floating point model that you originally had. So your test bench has the accuracy of floating point, and your design model, I'll call it, your HDL model, is the fixed point that's synthesizable. But the verification allows you to converge those two. So any loss of accuracy that you incurred, you can find out if you still meet your specs. Then you generate your RTL and the test bench, right, from the tool. You run your simulation, which is uneventful, more than once. Right? This is not a linear process, some iteration that goes on in all these steps. But you get to that point, you decide that everything's good, and then you go and synthesize your code, right? The actual FPGA design. So really, these three steps here are running in parallel with a development step and a verification step. So it has stuff. And I shouldn't even put the number there, because by the time I write the number, it's wrong. It goes up. It's way more than 180 now. Just probably haven't updated it in a year. So it has basic blocks with varying levels of synthesizability. These are just the kinds of things that you'd use in run-of-the-mill logic design. It has signal processing blocks, so all your favorites, FFTs, finite impulse response filters. A note here, this is kind of what I do all the time. This stuff, if you use the Xilinx tool, something like Vivado, Vivado has a library of signal processing elements, and you can design them at a high level. And I find that it's easier for me to design right in the tool and directly with the Xilinx. So instead of saying putting in an FFT in MATLAB, I can put in an FFT right in Vivado. And if I have a complicated design, I'm more comfortable, instead of having a huge picture that I have to navigate across to make these connections, I'm more comfortable just creating hierarchical HDL. And it comes out better. When you put in, so there's a Xilinx supported library in MATLAB. So if you pull that in and you say FFT, it basically does what you want, right? It'll put in the Xilinx FFT block. The problem is the stuff around it is a little cumbersome to design in MATLAB, and I'm very comfortable with doing it in Vivado, or I don't use the Altera tool much anymore. And then again, favorite communication blocks. This is the stuff it comes with. You could buy a whole bunch of other stuff from third-party vendors. Whoops. So we'll go through this list, and this is pretty much a mirror of the slide I showed a few ago that had the picture of the FPGA board on it. And with anything, I implied this right at the beginning tonight. It's one thing to have the tool and the language and the way to capture your design, but you have to stay within certain rails. So we have coding guidelines for HDL, and I talked quickly about them here. If you took the FPGA class, I talked about them there as well. If you took my software engineering, I talked about them, but differently. So it's important to not set people, engineers, loose with the language, but to put up some guidelines, right? because there's 10 ways of doing the same thing. This is the way we're going to do it. This is the one of those 10 or one of those 5 that we're going to use to do it. So this is loosely based on that. And we'll go through these separately. And really, this stuff is not detailed enough for you to have a best practices document. And we maintain a Verilog, HDL coding guidelines, a VHDL, HDL coding guidelines, a system Verilog, HDL coding guidelines for verification. We have tell me when to stop, right? Everybody who writes a language within our organization, I think, has some coding guidelines that they adhere to. So where did I skip, right? I hear that Rust is the language that software engineers have always been waiting for. One of the embedded designers that I respect said that to me about a month ago, and I thought, I better buy that book. I don't think we have coding guidelines for it yet, right? Because we're just starting to use it maybe in the last 6 months. So shouldn't there be coding guidelines here? And yes, there should be. It's hard. It's hard to write coding guidelines for a graphical interface, right? I can say, all right, if you want to develop a flip-flop, then write these 10 lines and it'll be a flip-flop. It's harder here. So let's talk about these as the guidelines for the guidelines. So number 1, convert floating point to optimize fixed point models. The tool will do this for you. You're very concerned in digital logic about bit growth. So as you do calculations on things, they carry out to larger bits. You multiply two fixed point numbers together, the result width is the width of the two products added together, right? You keep adding 1 bit. So there's ways of automating that, and that's what MATLAB does really well. So it creates bit true models in the same environment. So what do I mean by bit true? So if you I keep referencing it back, my FPGA class is running in the summer, in the fall. But bit true is what we did back in the FPGA class, where we were looking bit by bit in numbers and how the actual calculations were done. Because remember, math in logic is not math. It's a logic function that approximates math. So MATLAB does a really good job with that, but you have to tell it what to do. So for example, it's hard to read up here, but on the slides, it looks good. You specifically state for every fixed point number how many bits it is, how many bits on the left-hand side of the decimal point, whether it's signed or not. And the tool will allow you to manage that. The tool will tell you you can't do that. It won't fit, right? These two numbers multiply together, and it will come up with the result, but it'll be scaled, and it'll tell you that it's scaling it. This is the stuff you got to get right first. So number 2, automatically generate readable, traceable HDL for the designs. Now, every time I hear machine generated, I think unreadable. And I don't know, 10 years ago, I went down to Natick and I took the HDL Coder class at MathWorks, and they said, oh, do this design. And I put some stuff together from the book that they give you, and I pressed whatever it is, generate. And they said, oh, and there's the HDL code. And I remember opening it and thinking, this isn't that bad. So as far as machine generated code, it is reasonably human readable. Now, I've read some code that was written by humans that wasn't reasonably human readable. So in the long run, it's pretty good. So do that, read it. So when I synthesize something, and of course, sometimes I synthesize things that are thousands, millions of gates, but I always do some sort of netlist check. I always go in and at least spot check to make sure things make sense. You want to be able to do that here, right? So you want to have some human feedback in that, all right, I did this stuff. I want to do a peer review, right? That's what we do. So you create a a system design, you generate code with HDL coder, and then you do a static test of it. Right? So don't discount that. It's important, and don't let anyone tell you it's impossible. They even help you by putting comments in that references back to the original design. It also has things that you can put in for optimization. Now, that gets deep into the design process, but things like pipelining, logic replication, and those kind of things, not necessarily appropriate for the verification class. I stuck it in here because it was interesting. Area optimization, same thing. You can do speed, area trade-offs, and generally, as you make things smaller, they slow down, right? Because you don't have as much parallelism, and so on, right? It's about power. We've already talked about that a little bit tonight. So verification, 3 levels of abstraction, right? So we have verification of the model. So, notice that this isn't buildable. This is the block diagram in Simulink. And this is what we can verify. We can verify the requirements through this, that we've covered the requirements, I should say. We can do a functional, which we've been calling behavioral verification of it. We can look for equivalence. So ultimately, if this is a lower level of abstraction of our specification, we can take the HDL or the gate level model of this and do a logic equivalence test on it with the tool. We can look at coverage somewhat. The problem with coverage here is it's functional coverage, not gate coverage. It's kind of what we were doing when we talked about coverage back in the random stimulus and functional coverage. Property proving, yeah, maybe in virtual platforms, maybe in that we could create a virtual model of this. Okay, now this goes to this. Our HDL, so again, requirements, again, equivalence, because it's another model. We can get coverage of this, and the coverage is more applicable because now we're looking at the exact code that we're going to synthesize, and we can also insert assertions. Remember, assertions are things that tell us things about the code while it's running in simulation, and then ultimately we can put it into an FPGA. When we put it into the FPGA, it's another equivalence step, but we can do regression, right, which is in this case similar to it, but we make sure that the tests that ran on the HDL model also run on the FPGA. And when we do the FPGA, be careful the way this is written. When we do the FPGA implementation, we're going to do timing analysis. So timing analysis isn't taking a code, putting it in the FPGA, running at full speed, and seeing if it works, maybe hitting it with the freeze spray or something. No, it's the implementation process that runs static timing analysis. So that's the timing analysis that we're talking about here. So digital waveforms. We can't look at digital waveforms anymore. And I've said that, right? This isn't the goal here. So the goal is automatic checking, especially as things get complicated, and 100% coverage. So that's what we're looking for, right? We want to have automated tests so we don't have to look at waveforms, and we want to get a high level of coverage. 100% would be nice. So how much of this, right? The coverage, the equivalence, and the regression are automated, and we can continue to reuse this as we go through. So the tools for this exist within MATLAB and Simulink. We write the requirements, obviously. We look for the function of the chip, meaning the designers, but the tools to run across these 3 levels of abstraction, the behavioral, the RTL, and the gate level, right? Just remember that. That's what we talked about a couple times already. Behavioral, RTL, and gate level is much more seamless. Remember, this isn't always easy. So sometimes the conventional things, a lot of times the conventional ways we've been talking about it, is a way you're going to do it. If you have a design that fits well into the Simulink format, then this is the process that you can use. They'll tell you can do anything. And of course, you can do anything with the tool, but just because you can doesn't mean it's the best way. So be careful. Works very well in signal processing designs, in control system designs, places where you're doing a lot of step-by-step math. If this was a processor design with a bunch of peripherals, I would maybe use the autocoder to write my C code that's going to run on that processor, but I wouldn't use this to generate a processor. A communication system depends. Most likely I would, at least for the communication peripheral, because again, you're doing stream processing. And I've used this tool for signal processing design, and I've used it for communication systems. But the communication system, I'll admit, was kind of, it was a software-defined radio. So software-defined radio is a signal processing system with some logic at the other side that does things like error detection and correction and other digital coding, which again, this tool does very well. So the good news here is if we're automatically generating tests and the tests know the math that we're doing, we can generate a lot of tests quickly. They run fast, and if they don't run fast enough, we have that gate level model, right, that we can go down to the FPGA to go to directly. So is it going to be 100% coverage? Probably not. Is it going to approach that more quickly than if we had tried to do it by hand? Yeah, it would. So you can integrate this together. If we haven't really seen this, but this is a coverage tool. So this is the tree of the design. So the top level, internal levels below that, these are actual modules. And then these are the coverage of the model. So of course they show them all at 100%. But usually if you're in this dashboard and you tell the simulator run coverage and you open up the design tree, you see these grow, get to high numbers, but a lot of times you see one that isn't getting tested effectively. It's not getting stimulated, so you don't see that. So ultimately, this top one here, right there, that's the sum of the coverage of the whole design. So if you click the minus sign here, that would be the only line that was there, and this bar would tell you what the coverage of that, of the design was. But then to debug it, when if this comes out to be 56%, you get some work to do, and then you go down and look at lower parts of the design. That's a graph of it, kind of useless. We use system level test bench for HDL verification. Okay, that makes sense, right? So if we don't want to put the FPGA in the loop, we still have the iterated path where we can go between the model and the design. And in fact, this is a more conventional way of doing it, because what you don't want to get into, and I don't know if I really said this explicitly last week, what I showed you last week is a good idea to test things that would be hard to simulate. But what you don't want to happen is to have a parallel effort that's the FPGA design. So you have the ASIC design path and the FPGA design path, and it becomes two design efforts. I probably mentioned that I'm writing a book, and one of the case studies in the book was a time when I was an ASIC designer, and we decided we needed an FPGA platform for the software engineers to verify their software before we had the ASIC. And honestly, that became at least as much of a design effort as the ASIC effort was. In the end, it was mildly successful because of some other reason, but I learned that don't make the FPGA design hard. So you really do stay within this. And I think the designs that go, I'll flip back 2 slides, that go the whole circle are things like designs that have processors in them, where the software engineers want to be able to try out their software on some level of functionality. So here's the thing, right? So you have this system on a chip that you're building. It has processors on it and all the kinds of things that goes into processor design. It has an Ethernet MAC. I'm just using that as an example. You can spend a lot of time on an FPGA getting an Ethernet MAC to work, to get it to pass static timing, to get all the configurations right. And all they really wanted to do was make sure that they could run the software and they didn't get stack overflows, that they didn't go to areas in memory that were illegal, that their boot code would run. So the Ethernet MAC could just be a fake model, something where every once in a while they go and read it and it has a packet, even though it didn't actually get it from the line. So this outer path is much more common when you're verifying a chip that has a processor on it, because it gives the software engineers a platform well before the ASIC comes in. And you can't, might be a strong word, it's extremely difficult to run any amount of software on a processor in simulation. So we're working on this multiprocessor chip with a bunch of peripherals and everything, and we just last week rejoiced as a group that we got a transfer across the chip that was running on a piece of software that we loaded into it in simulation. Now we have an FPGA coming, and that will allow the software to do real stuff, but it was painful because when you compile code, and I'm not an expert in this, but when you compile C code, it, even barest of bare metal, it does things to set itself up. So you write C code that's write to this register and read from that register, right? That's the C code. So those two instructions. So main, open, close, a write and a read. So access a write access to an address, a read access from an address. So now you load it in to whatever, your simulator, right? So you have memory in the simulator that it's going to boot out of. So you take the code and you think, boy, that file looks kind of big, because you only expect it to be about 4 words, right? The 4 words are to, a couple words to do the load and then the store, and then the store, and then the load. And all right, we put the files in, and then you turn it on in simulation, and it's writing to RAM. What's it doing? It's zeroing out the whole RAM before it starts. I don't need that because I don't have a stack. But the code has to do things before it can get around to the instructions. So now 1,000 or more, many thousands it seems, of instructions, it finally gets around to writing that and reading that register, reading that register. But hours of simulation time has gone by. So now you got to knock on the software engineer's door, and they didn't even know what was happening. You get the idea, right? It's much easier to do it on the FPGA, but if things don't work on the FPGA, now you're dealing with the logic analyzer and things like that. So it's good to be able to do transaction in both directions in simulation, and then do your, load your drivers and get the peripherals running and all that stuff on the FPGA. All part of verification. So Verify HDL is another tool. So there was autocoder to generate C. There was HDL coder to generate HDL. And then very much like HDL code is Verify HDL. So Verify HDL is the tool that generates the test bench for your tool. It's very much the same tool. And it doesn't run it. You can do simulations on this stuff during development in Simulink. But what you really want to do, because it's your target, is to run it digitally. So here's your Simulink simulation, right? And remember this stuff? I said, if somebody gave this to me, I'd want to know what the chip was. It kind of done that here. This is like the boundary of the chip, these thin vertical lines. And then this is your response checking. But then, all right, it works, it's not dead, but then you generate it, and you generate the HDL code, and then you run it in ModelSim or QuestaSim. same thing. So if you have an FPGA in the loop and you're running tests, you can set a progression with this stuff. I've never actually used that. I would assume that it's pretty easy, right? Because you're generating all the tools here, and all regression testing is telling it, this is the list of test cases I want you to run. So the FPGA in a loop works really well if you have the right FPGA board. Might not even be the FPGA you're going to use, and you might be designing an ASIC. So, but it gives you logic acceleration, and it's more automated than the process I showed you last week, but it's probably more costly. Okay. So MATLAB Simulink Test Bench stimulus into the design and then produces results, right? So just this circle produces results. This stimulus and this reference produces the stimulus for the actual design. So this is the automatically generated test bench. This is a conventional test bench like we've been talking. The stimulus is informed by the stimulus that was in Simulink. Notice I'm saying informed by, not is, because it has to be converted into something that the digital simulator can use as a model, and then it's comparing it to the reference results to the actual results. Should all sound familiar. It's just a more automated way of doing it. So we're talking about this in, what, an hour or two by the time I'm done? You could go to a week class at MathWorks, and they would bring you through the examples. They'd have the equipment there. So if you were actually going to use this, especially on a big design, you'd have to own the tools. And when you own the tools, they generally give you education credits for it and take the class in this. Okay, so there's the two paths, right? The RTL path, I'll call it, and the gate level path. They're running in parallel, so we should be able to compare the results. So just, I'm going to go back. It's this, but there's two different models for the actual simulation. This one, oops, sorry, which is right here, and this one, sorry, I keep flipping back, right, which is right here. So just think of these as alternate paths. This is the same in both, right? The stimulus generation and the response checking. Now, obviously, there's some details that are different right at the interfaces, but you're getting the same results. And then, yeah, if you use one of those, this was music in and music out, some kind of filter for it. You could plug in something, a music generator, we'll call it an MP3 player, and you could put speakers on the other side. So in, all the, we do radio stuff. So we have signal processing that smart people come up with that we implement in FPGAs, and then somebody goes out with the radio in the field, they stand there with an antenna and a data acquisition unit, and they gather the radio data that we have to capture. We take that, we convert it to vectors, remember golden vectors, and we play them out in simulation. And it doesn't work, right? We tweak things, change filters, move things around, repipeline, and now it works. So then what we do is we take that design, put it on an FPGA, put an antenna on it, not that simple, but put an antenna on it, go out in the same field. Now we have something that we are much more likely to get real data from. We look at the antenna, we put it on, we have the integrated logic analyzer going, and we get more information, and so on. Transmission isn't as hard, right? Because you're not worried about any differentiation. Okay. So that's that. 50 minutes, right? And it would be a 40-hour class to go through the whole thing. You could look that paper up too. It's maybe slightly more explanatory. All right, so asynchronous design. And the specific case I picked for asynchronous design is clock domain crossing. So clock domain crossing is a case where you have clocks of different phase and or frequency that are generating and receiving a signal. Now, digital circuits want to be synchronous. So the guideline for developing implementable digital circuits is to have one clock. And in general, everything that you design has one clock, except you might have more than one thing that has to talk to another thing, and they have different clocks. So there are techniques for connecting them together. And I keep referencing it, but if you took my FPGA class, we went through all the techniques. And the bottom line of it was, but it's hard to verify. And here we are, right? So what do we do when we have something like this? And I can tell you, it's not good news. Meaning there's no automated way. There's no thing like, there it is, it works. There's a group of tools that put together will give you the ability to verify clock domain crossings. So we talked about what they are, and we know they're important, and we can design things forever, but we don't know if it works until we have some sort of feedback. Now, the hardware methods that I've talked about aren't even really perfect for verifying clock domain crossings, but at least they're more real. Here's the problem. A clock domain crossing is based on, or what you're trying to filter out in a clock domain crossing is the fact that you have two signals generated by different clocks that have a undefined but continuous relationship to each other. Continuous means something where I can't differentiate one level from another. An analog sine wave is continuous. So if I look at that, it could take on any value. And I measure that value based on volts. Now, what does that really mean? Well, I don't know what it means anymore because I used to know what it meant when I put an analog oscilloscope on it and the value was somewhat proportional to the value that it was seeing. Now we don't have analog oscilloscopes anymore. We have digital oscilloscopes, and digital oscilloscopes produce discrete results. It might not look it, they might filter it so to your eye that it isn't, but digital oscilloscopes sample things. Remember last week, right? So simulators are the same way. Simulators are discrete time devices, which means that a simulator doesn't continuously measure things, it discretely measures things based on the time scale. Remember the time scale from weeks ago. So we tell this thing that the time scale is a picosecond. And I talk about whatever your gate level models are modeled at is what you should tell the simulator. So if your models are have a picosecond resolution, so you have an inverter and the delay through the inverter from a low to a high is, say, 25 picoseconds. And from a high to a low, it's 32 picoseconds. I'm just making this up. So in that case, if the simulator is set to picosecond resolution, it will actually measure those exact times. Now, the reality is if I put that inverter in the lab, first of all, it's not going to measure either of those two values because those are temperature sensitive and process sensitive, voltage sensitive, but it's going to be an actual value. And it's not going to be discretely measured at those picosecond levels unless I have an oscilloscope that's a discrete time device. So the bottom line here is in the model, it discretely tells you where the setup time and hold time window are defined. And if you're on one side of it, you make the setup time. If you're on the other side of it, you get an error, right? And the error usually comes out as a console error in your simulator that tells you what flip-flop just had a setup time violation. How do I know that if I don't get those errors that I've designed my clock domain crossings correctly? You don't. Also, if I have those two clocks and they're different, I can't smoothly change them relative to each other. I can only discretely change them. So it's going to be one point where they work, one point where they don't work. The most important thing in clock domain crossings, in asynchronous design, is that indeterminate case. And that is what's going to physically show up. So you can't rely on the simulator alone, the digital simulator, to verify your clock domain crossings, because the models are based on discrete numbers, and the problem, metastability, is based on continuous. Now, if we went into an analog simulator, we'd have a better time with this. Because remember, these digital signals don't go like this when they switch. They go like this, and maybe they even go like that. The analog simulator will show you that. But it would just take forever to do an analog simulation of a million gate design. Literally forever, right? Where forever is defined as the useful lifetime of the chip you're trying to build. So, here's that thing, right? There's the signal changing too close to the clock, and this is what the output would look like, right? It would either do some weird thing on the rising edge, or it would go up and back down, and then up on the next cycle or something like that. And what we do is we put in 2 flip-flops. I have to tell a quick story. You've heard of ChatGPT? I completely ignored it. And the other night, it had nothing to do. So I downloaded it and did, whatever you have to do to register. And I asked it my interview questions. And I'm sorry to say, I would have hired it on a phone interview. I asked it what the setup time was. It did it. I said, what happens when you have 2 different clocks? It basically explained this picture to me. Somebody, and now I feel like I've been scammed, that I've asked people questions, and in a phone interview, there can be someone on the other side of the camera that you don't see. But looking at this, and I feel safe talking about this today, looking at this, I realized that this could talk a good game. And I, next morning I called up one of my colleagues, and I'm like the design interviewer. I'm the hard guy to get past. And then he's the verification guy. So he's the guy who asks the hard verification questions. Sometimes they give us an hour together, which is a real blast for the interviewees. And we've decided we have to come up with a set of questions that would be hard for ChatGPT, but someone who is good at this would be able to answer. So how do we come up with those questions? Someone has to say it. Ask ChatGPT to come up with the answers. So now I feel like, and that's why I said I'm comfortable saying this today, because all the homework's in, I feel like maybe not in this class as much, because you have to write code, although I've seen code that comes out of this thing, and it's also pretty good. But in my software engineering class, I know now I'm getting scammed in that class. The people are just using it to answer the questions. So I got to work on that. Not a problem I ever thought was. So in fact, the guy who was the verification interviewer, he said he gave it a few lines of text and it wrote a song for him. And he said the third try, it was pretty good. But anyway, you should be able to do this without asking ChatGPT, right? So the receiving clock domain has 2 flip-flops. And a lot of times in ASIC libraries, there's a cell with 2 flip-flops in it. So how do you do it? Flat verification. You read the code. This is an option for white box testing. So if there's a clock domain crossing, a verification engineer goes into the code and verifies that the transfer between those clock domains looks like the picture I just showed you. An output clock, 2 clocks going in. There are tools, by the way, too. So these tools like Lint and like Spyglass that are code checking tools will flag a lack of clock domain crossing. They might say it a little differently. They might say there's logic here, right? But you have to read that as you have to go through 2 flip-flops before you can go to logic. But there are tools that on the flat design will be able to do it. Now, you can do it in a black box, right? Where the black box is our term of black box, where the verification engineers just run the simulations on it. And if they see a setup time failure, then they flag it. what a verification engineer is going to do? They have two clocks. So if I have two parts of my design, they both run at 100 megahertz, the verification engineer is going to take one clock and send it to the 200 megahertz clock, and everything's going to work. So black box might not work as well, but a gray box is better. So gray box is, these two clocks do converge somewhere in the design, so do something with them. And we talked a long time ago that there are ways of modulating the edges on clocks. So you might have a 100 megahertz clock and a 100.001 megahertz. Be careful when you say 100.001 megahertz, because that comes out to a number, because simulators are time-based, not frequency-based. So when you say that 100.001 megahertz, take the reciprocal of it, and that'll tell you how many picoseconds that is. Because if you're in a picosecond resolution, I'm not answering a call, I'm calculating this. I don't have a reciprocal, sorry. I thought this would be easier. That's 999.99, 100.001. What does that say? It's going to round off. It's not, it's going to come out to 1,000 picoseconds. Ain't going to work, right? So when you define that slightly different clock, make sure that the simulator isn't going to round it off to the same period as the other clock. You might even put some randomness so you modulate the period a little bit. Bottom up, right? So you actually go down and look, or top down. So these are, black box, gray box, white box. I think of the bottom up method as looking at the outputs of a block that's given on a certain given clock, and then the inputs of the other clock domain, or the other clock, and actually going signal by signal, or making sure that designers are doing what the guidelines say. So part of your coding guidelines has to be this picture, right? And you might even, our coding guidelines has this picture in it. It actually has a picture from the Sutherland paper. And then it has a piece of code, right? Just actually shows the code. So make sure this stuff is there and it works. Now, I wouldn't have every verification engineer looking at one little part of the design. If you're going to really expose this and really get into the white box method of verification, you have one person who specializes in that. Also, I think of the tools like Spyglass, Lint, right, the static verification tools, as being white box testing, because they're looking at the code and they're looking at every detail of the code. Now, so here's the thing. You run the tool, and it comes up with 4 places where there's a clock domain crossing. And you say to the designer, there's 4 places where there's a clock domain crossing. And the designer says, oh, I don't care. The timing is such that that will never be a problem. And you don't just waive it, because it's always a problem. Because no matter what frequency you're running at, no matter what the disparity between those two frequencies are, if you get into a metastable state, it over time will propagate into the design and cause another problem. So every clock domain crossing, no matter what the designer thinks, has to be fixed. And my response is, hey, we're not going to take that extra flip-flop out of your pay. So structural, right? Make sure that just every place you blindly put in, that would be my first one, the highest priority. Sometimes you have a case where sometimes the next state can handle the potential of an unknown state coming through. This is very rare that the protocol will actually handle a metastable state. And it looks like it would in a lot of cases, but the problem is that metastable state can propagate. So here's an example, best example. you have an interrupt on a processor. It's on a push button. So that push button is completely asynchronous to the design, to the clock. So someone says, well, yeah, but the interrupt can happen at this place or this place. But the problem is, if the interrupt actually sees a metastable state, that metastable state goes into the state machine of your process and puts it into some odd state. It crashes, right? So protocol doesn't work. And then metastable verification. So if you did get in, so even when you put a metastable filter in, even when you put the dual rank flip-flop in, there's a chance that the metastable state could still go through. So what you want to do in addition to this is have logic design techniques such that a metastable state wouldn't cause damage or it would limit the damage. So as an example, if I have a state machine and the state machine has 6 states, but I have to code that state machine into 3 bits, right? Because that's, you know, how many you need. That means you have 2 extra states. You do something with those 2 extra states. So if you accidentally got in one of them, you would return to normal operation, right? So that's metastability. That's extremely difficult to test, by the way, because you're testing a state that there's no legal way to get into. So how do verification engineers deal with that? I don't know, but here's the worst problem. If you deal with radiation-hardened systems have to be designed expecting that there's a probability, a reasonably good probability, that a flip-flop is just going to change state. So you have to put in extra logic that will handle that. And I'll give you an example in a minute, but what happens is you do that in your code, but the synthesizer looks at it and says, oh, you don't need this. That's redundant. I'm going to take it out, and it optimizes it out. Then you think you designed it in, but you really didn't. So how do the verification engineers test that? How do the verification engineers randomly flip the state of a random flip-flop in the design? It's hard, right? But it's something that somebody has to test. So just as an example, FPGAs are, it's not as bad as it used to be, but it used to be virtually impossible to send an FPGA to space because they're SRAM based, and SRAMs are particularly susceptible to alpha particles. And the atmosphere filters out the alpha particles, but of course, when you're above the atmosphere, there's no atmosphere to filter out the alpha particles. So they hit the SRAMs and so on. So Xilinx came out with a rad hard FPGA, and it was 50,000 gates. I might have the numbers a little off. And they said it was exactly compatible with another part. The other part happened to be 150,000 gates. So here's the math. Every flip-flop in the design was triplicated. And the output of the flip-flop was measured based on best 2 out of 3. So every flip-flop, this is the factor of 3, the 50 to 150, every flip-flop in the design was really 3 flip-flops. When you had the output of the flip-flop, there was a gate on the output that would decide, majority, best 2 out of 3. So almost all the time, the 3 values would be 3 1s and 3 0s, but every once in a while it'd be 1 1 0 or 1 0 1 or something. And the logic would do 2 things. It would report the right state, and it would rewrite the flip-flop so whatever one was wrong was righted. How do you test that? It's hard. How do you make sure it's still in there? You spot check for it. Meaning, so if you put that in a synthesizer that didn't know what it was doing, it would simply take 2 of those flip-flops out. Because the D input of all 3 flip-flops is the same signal. So identify blocks, right? Know the boundary, and document the requirements. Like I said, make it part of the coding guidelines, especially that circuit that I keep showing, the output flip-flop to the 2 input flip-flop. And define the rules and define how it's going to be tested. Formalize exceptions. So this is my favorite one. Anytime there's a warning that comes out of one of these static tools and the designer says, oh, that's okay, the verification engineer says, well, you have to fill out a waiver. And it's 14 pages long. I'm exaggerating. But you make it really hard for them to get a waiver. And what does really hard mean? A little harder than it would be to just fix it. And magically, these things get fixed. And then define goals. You can't show coverage on the thing that you can't replicate. So this is kind of busy, but you have your RTL, you do the structural analysis on it, how they connect, the formal analysis that does that internal, looking at all the gates. And, you can do it in this debug GUI. Simulation metastability injection is hard. And I say it's hard specifically because there's if you have 100,000 flip-flops in the design, all right, you don't have to do it on all of them, but if you have 200 signals that pass between the two, there's 200 places where a CDC event could happen. So if you have logic in between, you can have errors in the logic. Important to know. I'm going to sneeze, sorry. This is a pretty good paper. Reconvergent, right? So you have two separate paths. This is a bad idea. The last thing that comes out of a given clock domain should be a flip-flop, right? You shouldn't have logic after the flip-flop that's going into the flip-flop of a different clock domain, right? This is the first time I've explicitly shown this. The other cases, it's all been happy, a flip-flop that goes to two flip-flops. It has to be that. It has to be a flip-flop going to flip-flops, no logic in between, especially logic that's fed by potentially two different clock domains into a third clock domain. Bad idea, right? Define your clock domains clearly. No logic in between. If there's no logic in between, it has to be one clock domain to the other anyway. Can't have, because the logic is what we're combining. This is from the Cummings paper. I called it the Sutherland paper before, but the Cummings paper. And this is like the paper to read about clock domain crossings, even though it's getting old. Logic design is logic design. He does a really nice picture. You see these pictures in a lot of other literature because people just copy it. But it shows, the two steps. This didn't copy well, but the output flip-flop into the synchronizing flip-flop into the flip-flop that goes to the final design. So you can simulate this by varying the delay value. An important thing, sometimes in simulation, you have a different model that you're using than what you synthesize. That can help you simulate other parts of the design, but ultimately you always need to simulate what you're synthesizing. That's what this if-def does. So this is what you're synthesizing. This is what you're simulating. Ultimately, you always have to do this, but this one you can muck around with delays and how things are going to try to force metastable states. Just think of what it would take to do this to 200 signals, for example. Okay, let's take 743, 755. So let's come back at 755 and I'll blast through these last slides and then that'll be it for tonight and then we'll do a review next week, but I'll talk about that. Before you ask, the in-class code is 1606. The virtual code is 4356. So in-class 1606, virtual 4356. All right, see you at 755. One 606. I was getting scared. I was going to have to talk to an empty room until you walked in. All right. So enough people told me that they got jobs um, based on what they learned in this class, that I thought I should emphasize that. And some people take this class because they have a job and they want to learn more, but they interview people who want to get in here. So I thought this was useful for both cases. And I'll tell you the truth. I did all this, and then the next time I gave it as a class, it was contracted by a company, so everyone worked for the company. And I got to this, I thought, oh, this is a little odd because I'm telling people how they could get a job and leave the company. So that's when I added the stuff. Well, maybe this is a way you can create interview questions. So for entry level, right, there's certain things that you'll likely be doing, things that you'll need to know. I would hope that the background that you got in this class is almost everything you need to know. The one piece that you don't have enough probably is UVM, because UVM could have been the whole 14 weeks. So to really learn UVM is a 40-hour class. And if you've been counting, we've had about 40 hours of contact, not even that, in the class. So that would be an on-the-job training kind of thing that you would do entering in. But knowing Verilog, system Verilog, digital design, and then the kind of the structure of how it goes together would be entry, right? So now you get into the case where you are doing more of the architecture of verification. So it's more a case now where you understand the DUT better. You might contribute to the spec development, and you might be the lead of the verification effort, right? I maybe not saying the lead of the verification group, but the lead of the effort. And you've heard me use the term, if you were the verification manager, as I went through, I'm meaning the person who's managing the effort, who's keeping the schedule, who's reading the spec and making sure the right test cases get put together and so on, right? And maybe managing people, but that's another class. So you create, review the verification test plan based on the spec, and then higher levels of experience. I don't know if these numbers are right, but you get the idea. After you've been through that, then you're maybe more of the engineering manager. So you have a group of people who are running verification efforts. You're likely to set policy. So when I talk about guidelines, when I talk about picking tools, that's that higher level position. So the first tier is someone who comes in and is doing coding work and has to know the code and the interface and how logic works and be able to credibly read the spec. The next tier is someone who manages the verification effort. Now, in a small verification effort, this could be the same person, and they manage the schedule of the effort. They decide what test cases have to be written to implement the test plan, and they probably write the test plan in the first place. And then the next level is someone who administers the verification effort at the company. So they're the ones who potentially hire the people who are doing the work, and they set policy for how the work gets done. And they probably are the expert reviewers for things like specifications and verification plans. So here are some interview questions. I didn't run these by ChatGPT. So what's the difference between SOC and IP verification? It's a good question. What is a multi-clock domain design? I might use that in the design interview as well. Consider simple memory model, explain the possible verification scenarios. That's good. Write me that's something you could do in a 30-minute interview. Here's a memory, right? Have a picture ready, especially on virtual stuff. So I do that clock domain crossing thing. And I have my little library of things in Visio. So when I ask somebody a question, I could flash it up on the screen. So we're not trying to hold paper up or draw on the screen in real time. But a memory is a great one because you got to think about different test cases for it, if you will. When is verification done? This is an excellent question. If they say when the schedule says it's done, then they go directly to management. What's the difference between IP and verification IP? It's good. I might expand on that significantly. Now, maybe these are earlier career people and these are later career people, right? Just because you expect them to have some experience. Because now we talk about, anyone can define those two terms, but how does that fit in? So we know how we use IP in design, right? We get a block that we don't have to design, we plop it in, reusability, right? Well, how does that work on the verification side? What is best among IP level and SOC level verification, the level of detail? How important are code reviews? I bet that wasn't on the list and I added that one. So this www.verificationguide.com. So this came from a different place. What skills do you think verification engineers need to be successful? How did I do? Demonstrates the candidate's understanding of the role and highlights pertinent skills. It sounds like a ChatGPT answer. What information should be gathered before developing product testing methodologies? Sometimes I think the people who write these answers aren't really verification engineers. What techniques should be used when designing product testing equipment? Okay, we might be a little off on that, but you can expand on these questions. How would you ensure that your testing procedures exploit product's weaknesses? This is the one when you have the 10-year person in front of you, you ask this question and you take notes because they probably come up with something you didn't think of. What verification protocols did you design and implement in previous position? I'm asking that. So if you believe it, right, design projects kind of all go up, right? This hasn't been updated in a while. Percentage of product time spent in verification. 61%. It's a lot. I guess I didn't look at that right, but still a high number. Mean peak number of engineers on a project. 10-ish. 11, 12, I believe that. Meantime, designer engineers doing design versus verification. Design engineers doing verification. This depends on the corporate culture. Some large corporations, design engineers spend zero time on verification. They might run unit tests, get their stuff working, but zero time on verification. And the verification engineers spend zero time in design. Smaller companies, smaller groups, even, we're a fairly large company. Verification engineers do design work and design engineers do verification work, just not on the same program. So, this is about 50-50, right? But it really is a bit more specific to what you're actually doing. So verification spend most of their time debugging, followed by creating tests and running simulation and planning, right? So that's what, 34%? So planning and creating test benches design is the other half, right? These three are very related. 3% on other. Chatting with your buddies around the coffee maker. Services. So that was interviews and business and things like that. You don't have to verify your own stuff. You can hire a hired gun to come and do it. And this in silica, I should always check to see if these places still in business. Probably bought by somebody by now. So planning, feature extraction, capturing function cover, and checkpoints. A lot of what we already talked about. Architecture support of UBM, assertion-based verification, metric-driven verification. There's 3 slides here. It's going to be a lot. Formal verification techniques. So basically, they'll do anything you'll pay them to do. So this is a return on investment. They're not cheap, right? They're billing probably, between $250 and $500 an hour to come in and do the things that you might have to learn to do, then do. If you're only going to do it once, it might be useful to hire a firm. And they're definitely not the only one. I just took this because there's the most things on the list. They'll create the wrappers, interfaces, reference models, regression management, basically anything. This is an outline of the class, right? The stuff that I'm showing you here. So you have to interview them because maybe they're saying, oh yeah, sure, we'll do gate level simulation. And then they go and figure out how to do it after they're on the clock for you. Register abstraction, always on agents and protocols, cycle accurate, I can talk about those, but cycle accurate behavioral models, programming language interfaces, end-to-end verification closure for specification to RTL sign off. So, I don't know, if you're a fabulous semiconductor startup and you hire 5 designers to design your next greatest thing, do you want to, and that's your like secret sauce, and your secret sauce is embroiled in those 5 people. Do you want to hire a firm like this and give them $1 million of your hard-earned venture capital money to do the verification for you? I don't know, right? That's return on investment that you have to figure out. If you're not, so I picked that example because I think it's the most likely customer for a place like this. And why do I say that? Because if you're a large organization and you're thinking product line, you're going to want to reuse your code and you're going to reuse your verification IP as well. So you want to create the whole engine. If you're trying to get something out of the chute quick because you need to start making money, this might be an investment, but then you don't have the money to make the investment. Right? So I just want to show you that it's available. And I'm implying that this is complete turnkey, and it is. You could get help in various levels of consultation. And I wasn't joking at $250 to $500 an hour, right? So $1 million can go away. Let me think about this. 2,000 hours a year. So if it was 250, it'd be $500,000 per labor year, right? So if they have 3 people working on this for 6 months, you're in it for, that's at $250 an hour. You're in it for $750,000, right? It goes by quick. I don't think I exactly calculated that last number. A lot of money. Spec review, hardware, software, code verification, yep, availability of in-house verification techniques and knowledge. And, you know, I taught you the techniques. You need some experience in using them, but they generally have like the whole tool chain set up, right? They can just dump your design in and start building. UVM also, UVM is good, right? It's a good way to set it up. They have their tools. You want to make sure that their tools are compatible with your tools, because they're going to find bugs. And when they find bugs, you're going to have to repeat the bugs, and you have to have the same platform that they found the bugs on. Special things. If you're doing like, you know, we some years ago did an implant, and we had to do FDA testing with no clue how to do it, and we hired a logic verification firm to verify our code. Now, this is how we stacked the deck. We verified it first, so we knew it would fly through their verification process, but they knew all the forms to fill out and all the hands to shake at the FDA to get us approved. There's value in that. And we've never done another chip that was going into an implant. So it ended up being a good decision because we didn't have to build that engine for ourselves. Resource, schedule, cost, implement. Yeah. ASIC flow, again, from them. I'm not going to read all this stuff, but 4 steps: planning, the first stage where they're just seeing if the thing is alive. Next stage, they're more exhaustive about it. And then finally, they make sure they have full coverage, make sure all the bugs are closed, right? So the first stage doesn't work at all. Next stage is trying to get full coverage. The final one is filling all the final holes. They call it phase license stage. The different company, Aldec, this is not a consulting firm. This is a tool vendor. So Aldec basically gives you the whole platform. Insert your design and intelligence here. So they have tools for planning, tools for linting, and CDC analysis is the stuff I talked about tonight, but it's an automated tool to at least show if you have it in there or not. Simulation, emulation, I haven't used that word, but the process of using an FPGA platform to simulate your design is called emulation in a lot of areas. And then at-speed testing, and then finally prototyping. Depends on if it's an ASIC or FPGA tool. Mentors thing, right, to sell you their tool. So verification planning, functional coverage, metrics. So take this stuff with a grain of salt because they're only trying to sell you the simulator and they're adding all this stuff around it to make it more attractive. Mentor is the place that you go for the calculation engine. But they have to differentiate. No one can say, hey, this thing allows you to put your models into it, and all it does is calculate the logic as fast as possible. Right? So they can't. Every simulator does that, and most simulators are very accurate. So they have to add stuff around it. I used to work with a guy, and somehow we had business cards printed out, and somehow he got staff cynic as his title. That's the way I explained that. It felt like him. Best practices, right? This just comes from some site that I saw that is a training place, but planning, execute, actual functional verification, lab verification, and then the last bullet is support. None of these have any specific knowledge, but I've shown you like 4 different flows through this stuff, and they all have the same components to them, and they're from different companies or different. Verification Academy is a place that you can take, professional education kinds of verification classes. They teach UVM and that kind of stuff. And this is their picture. So if you had to create a picture like this for yourself, look at all these pictures and then create one that's customized to what you need. Okay, and then the final. So that's it for tonight. Next week is all virtual. Thanks, guys. And then 2 weeks from tonight is the exam. I'll talk about, I had people show up for the exam and there was big alert that everyone had to be in class. I'll talk about that next week. You got the code even if you weren't in class, and I emailed the exam. A couple people had problems being in the room with the laptop and stuff like that. That's the whole goal of having you take the exam on your own through email. So it's always worked well in the past. So you kind of get what I'm implying there. But we'll talk about that next week. So all virtual, and be there, right? If you're watching on the recording now, like you're not watching live, but you're watching this sometime later on the recording, and I'll encourage you in my email to get on Blackboard at 6:30 next week. And then the other thing, if, for example, we were to go all virtual for the exam, be on Blackboard at 6:30 because that will be the only way you'll get a code. Okay, the attendance code. I'll give the attendance codes at 6:30. But if you think 7:30, like, oh, I forgot, I won't be on Blackboard anymore. Last chance for questions for tonight. Okay, so you'll get an email from me, but next week's class will be all virtual. No more questions. Thank you.